All right, good morning. We're going to have a very interesting talk today. The speaker for today is Dr. Greg Rodgers. He's an AMD fellow. You know the company AMD, right? One of the two most important chip designers, okay, in the world, okay, next to NVIDIA, right? And Dr. Rodgers is going to give a talk on Exascale programming with OpenMP, right? And this work is important for AI, all right? So let's welcome Dr. Rodgers.
Thank you. Can everyone hear me okay?
For his interesting talk.
So, okay, full disclosure, why am I here? Right. That's why I want to make it clear why I'm here. First thing is, I'm not interviewing for a job. So, however, you know, I can tell I'm pretty close to retirement. I might entertain university work in the future. So, right now, I'm quite busy at AMD, leading our compiler development team. And I'm going to do one chart on my background since I've been working for many years. I'm not recruiting, sorry. I hope this doesn't empty out the building, right? So, however, my team is an important part of the software team, and we are hiring. So if some of the stuff you see today is interesting to you, or you're working in this area, especially in low-level compiler details, I'll talk to anybody, right? Especially if you have any experience building compilers like GCC or LLVM. Okay. So, no interviewing, no recruiting. I'm not here for that. Why am I here? Oh, I'm not here for the cookies either, right? Unless, you know, we want to have some fun and have a continuous glucose monitor. We can try to see diabetes. We can see, you know, how it sets off with some cookies. We can try things and see what how that works. So why am I here? This is why I'm here, right? These are my two grandsons. My daughter and son-in-law just moved here he's going to attend law school here, and they're very new to Kentucky. I'm new to Kentucky, and if I want to visit these guys, I have to come here. So this is why I'm here. Any chance I can to visit these guys, Nathan and Casey, I'll come here. So that's that. All right, this is about my background. I spent 28 years at IBM. The chief architect for the Mare Nostrum supercomputer, a lot of other stuff there. Oops. What happened here?
There it goes.
Back? Okay. I worked as an adjunct professor at University of Purdue, where we led the network for earthquake engineering simulation, the actual simulation systems that they had. We developed a data science course with Purdue University and University of Stavanger. And then in 2013, I started with AMD Research to research exascale computing. So in 2013, we were pretty far from exascale computing. And there was a lot of serious concerns. The Department of Energy funded AMD to do research. And some of the big things were, how were we going to deal with that much power? The budget at the time in 2013 was 30 megawatts of power, right? And they actually relaxed that into two supercomputers that are exascale. The first one being the Frontier Supercomputer at Oak Ridge National Labs, the second being El Capitan at Lawrence Livermore. They both have a 40 megawatt power limit, all right? But my focus there was on the programmability. How do we scale our applications to exascale? And I have 3 daughters and 4 grandchildren. This must be right. Intel processor. Very good. So I want to start with the survey to see here what kind of audience is. And he stuttered on the word OpenMP, so that kind of bothers me a little bit. All right. So how many of you here have used MPI before in software? Good number of them. All right. MPI is necessary. It's still very necessary to get to the exascale. All right. And we'll show some of that. How many of you have used CUDA? Ooh, nice.
We use compute shaders.
Shader compilers, you work with the shaders with CUDA?
But there are 3 ways.
Okay.
The CUDA, OpenCL, and the compute shader.
Okay.
We use compute
So we're going to talk about this a little bit and try to classify those as grid compilers or grid computing, all right? So how many of you worry about coherence, right, when you're doing this? So we got a couple there that they, and then how many of you have programmed a parallel reduction? A couple of you guys, right? Because that's kind of important, especially with some of the AI software. So our agenda is OpenMP programming model and why we care. I'm going to talk about Exascale, how we use OpenMP to get to Exascale, right? I'm going to give a little bit of internals for the LLVM compiler, and then I'll show how the compiler fits into the stack, all right, including it's a very volatile stack of software that sits on top of the compiler and the runtime, because it's just what's happening with AI. There's a lot of changes going on there. I'm not that familiar with it. I'm really stuck in the lowest level of the software stack, right? And then, just for fun, I'll get a chance to show you some of the things that are coming up, especially for next year in terms of our hardware. And you'll see that the AI is driving rack-level solutions now. Before this year, AMD and Intel, we've been a vendor of mostly parts, CPUs, GPUs, and that's changing now because in the area of AI, because of the scale that we need, we're now building whole rack solutions, including the networking. So it actually motivated the need for AMD to expand into buying Pensando for network processors and things like that. So, okay, OpenMP, all right. Unfortunately, I need to read here because it's put together. This is really what it is. It's a specification for compiler directives, library routines, and environment variables, right? The current spec is OpenMP 6. You can see it's like over 600 pages, so there's a lot of detail in the specification that actually grew from OpenMP 4 to OpenMP 5. We added tools interfaces and debugging interfaces to the OpenMP spec. I am AMD's representative to the OpenMP standards. A number of companies are involved in the standard, including also the national labs are driving a lot of the development of OpenMP as a standard. So it's not, if you used OpenMP, if you're as old as I am and used OpenMP 20 years ago, it's a lot different today. We have heterogeneous memory allocators, we've got acceleration on GPUs, and let's see. Okay, so this is like an example. I mean, this is in white down here in this code is traditional code for doing a vector multiply. Then you annotate the code with some pragmas to say that these iterations can be run in parallel, right? So why OpenMP? 3 reasons. If you've ever heard of the 3 Ps of what the national labs do in terms of assessing programming models, productivity, performance, and portability, right? This is very similar, right? First, OpenMP is comprehensive. We want something that can be used for all types of parallel programming, from vector processing to GPUs to multiple CPUs. We want something that's portable. It's interesting to note that software often outlasts generations of hardware. So software is harder to change than hardware, right? You would think the opposite. But a lot of times, especially in the area of simulation, where engineers and scientists get confidence with a certain model, those models and that software will exist for million generations. It's also why I was asked to lead a team to build Fortran compiler. There's still a lot of Fortran simulation codes out there. So yeah, our compiler is doing Fortran, and it's doing accelerated Fortran on the GPUs. And ease of use. I'm actually going to give a good example of doing a reduction, right, with CUDA and HIP versus how it's done with OpenMP. And you'll see, I hope you all agree, it's far easier to do some of these things with OpenMP. Okay, so OpenMP, traditional, it's a fork join, multitasking with threads. It also supports vectorization when you have a vector engine like AVX. And it also, now it supports offloading. So you've got to break your domain, your application domain, up into teams and threads. You've always had to break it up into threads. To do any kind of parallel processing, you broke your your domain up into threads, like whether each simulation of an atom could be a different thread, right? So, but now we must group those threads together in teams, and then put them together on devices, and then put them with ranks. So we're going to show the 5 levels of parallelism that application programmers have to deal with, right? So the OpenMP memory model, let's talk about this. If you ask Google, it says the OpenMP memory model describes how memory operation in a parallel program are ordered and made visible, right? It is a weak, or is a relaxed consistency model. That means you write your code, and when you say target region, the variables in there can be, first of all, distributed, one for each thread, and then at the end of the target region, that's when consistency is maintained. So if you have a vector or something like that, different parts of the vector can be updated in parallel, but then at the end of the target region, that's where you have the consistency, where you get a synchronization barrier there, right? And an example of the relaxed consistency is that if you have a scalar, you don't want every thousands of threads and GPUs accessing one memory location just to get a value that is typically read-only. So scalars are what they call first private. It's its own piece of memory within the target region, and first private means is when the region starts, it gets the value from the host or from the non-target region, and then it has a separate address, so that way you can get the performance of actually turning that, in many cases, a first private variable becomes a register, right? A scalar register. So OpenMP5, there's just, to try to get into the details of the specification, I want to just point out some of the highlights that are out there today. In OpenMP5, we have a unified shared memory or unified shared address model for those systems that support a virtual shared memory between the GPUs and CPUs, right? So they have this model that says, hey, ignore what's called a map clause. A map clause is a way to tell the compiler that array or that variable is going and how it's going to be used inside a target region. And what happens is, without unified shared memory, like you just have a GPU that you plugged into your machine. Without that, the map clauses will tell the compiler that I've got to copy these variables in or out, and what direction is necessary. Sometimes it's and also for allocation, you can just say it doesn't need to be initialized; it can just be allocated. So you have these map clauses, but in a shared memory model, that implicit copying that happens under the covers in OpenMP, it doesn't happen at all. You get the performance of having the unified shared memory, and what really happens in that case is the GPU touches the memory, and you get a page migration. So that's what you have under these newer systems that support unified shared memory, both the Frontier Supercomputer and the Lawrence Livermore. Those systems have unified shared memory between the GPUs and the CPUs. I'm going to get to a point to talk later about what's really becoming more important, especially in AI, is the linking between the GPUs. The communication, the bandwidth and latency between GPUs. It used to be between the CPU and the GPU. That's still important, but what we're seeing now, especially, it's also leading the design of some of the newer supercomputers to get that, GPU to GPU communications. Okay, so this is fork join. This graph over here really says, you hit a parallel 4 in OpenMP, it spreads the iterations of that for loop across the threads that are available to it. So and the compiler and runtime do that mapping automatically. You don't have to say how many threads are running. You'll typically get the most that's available, but then the compiler will make sure that every iteration of your for loop gets put onto a thread, a hardware thread, And there are different scheduling algorithms as well in OpenMP. But this is what fork join is doing. It's mapping the iterations to different threads. And to do this, this is code without this. This code here is OpenMP 4, OpenMP 3. This has been around for 20 years, right? To be able to parallelize this on multiple CPU cores, right? But to do this on a GPU, this is all you need. You just say, put that all within a target pragma, and it says, put this on your accelerator. Right? All right. So here, when you do that, this is what you get. When you have the pragma target, and you were mapping arrays to the GPUs. So in a sense, you have multiple CUs here running more in parallel. So you can see the hierarchy, the parallel hierarchy being initialized there. All right. The other thing that you have in OpenMP is the ability to do tasks asynchronously. And why would that be useful, right? So that you can leverage so that your algorithm may not be bulk synchronous. It actually could describe a task that is dependent on some other data being generated ahead of time. So the system in a runtime will schedule this if you say no wait, and it'll just be run in the background. And then you'll have a pragma-OMP wait that I guess we have a laser here. At this point here, all of the tasks that were generated here you wait for it. That's like a synchronization point, so that these target regions on multiple devices can be executed. Okay. I held that button too long. So yeah. So this is kind of demonstrating multiple devices, right? So a GPU device, those people who have used it before, used CUDA, you're aware that it has work groups, all right? Or what they call, and NVIDIA calls it SMs, right? So each SM runs independently, and that's what these represent, those SMs. And you want to run all of those SMs. This here is one SM, and it's multi-threaded with the warps that are on there. I'm going to try to avoid using the pointer. Okay.
Is that one?
All right. So you can see we've got device level parallelism within a work group, and in OpenMP that becomes a team of threads. In parallelism within the team, each thread is running in parallel, right? And in the case of, if you understand what a warp is from CUDA, a warp on NVIDIA is 32 lanes, a warp on AMD is 64 lanes. Until next year, we're going to be 32 again. But in any case, that's a little bit about how those three levels of parallelism within a GPU, or a collection of GPUs. So this is kind of a history lesson, right? For those, what you had, MPI was really the first major use of standardized parallelism, and you were a certain rank, and you knew how many ranks there were. That let the application figure out what work it's required to do. So you do that. With OpenMP plus MPI, you have the rank, and then you have a thread of the number of CPU cores. Now, this is with OpenMP before GPUs, right? So that was, so when you had multiple cores in one system, you're able to use OpenMP to leverage those two types of parallelisms. But with acceleration, you have a rank, a team, and a thread. Right? So this is kind of pre-Exascale. You had rank, a device. So now we had we had systems with multiple GPU accelerators. That was mapped as a device. And then you had a team, and then you had the item within the team size, right? So Exascale, this is what Exascale is, right? We now have full racks which have tightly connected switching within a rack, and so those became groups of MPI threads, right? So what I'm saying is, to get to Exascale, you've got to decompose your domain into these 5 different levels. It's not easy. You have to be an application programmer to understand how that happens. And that's the simplest model that you can get for Exascale. All right, Exascale. Go back. So what is Exascale? It's 10 to the 18th operations per second. We're typically using gigahertz speeds, billion cycles per second, okay, on a GPU, and in some cases up to 2 billion cycles per second. And so that means we need about 10 billion way parallelism to get to Exascale. To Exascale being 10 to the 18th operations per second. Now, true Exascale, the national lab where they're doing simulation, means that those operations need to be double precision floating point. That makes it, and that's not so true today in AI. In fact, you're going to see a lot of different data types and even mixed precision you're going to see with AI. So I'm not sure why this isn't up here. Okay. So 10 to the 18. So we're gonna ignore the frequency, the billion operations per second, the frequency for a second. Let's talk about how do we get to 10 to the 10th operations per second in parallel. 10 to the 10th parallel operations, right? We're gonna talk about that. So what's interesting is you've got to split this up between those 5 levels of parallelism that I showed you earlier. How are we going to get there? And I'll try to wing it without a slide. So within those 10 levels of parallelism, you have to get to 10 to the 10th to really call yourself Exascale. And that's how much hardware you have. If you have the whole computer system, the whole Frontier system, what really goes on a lot of times at both Oak Ridge or Lawrence Livermore, not all applications have that kind of scalability yet. So it's kind of a load sharing system. They'll actually have many nodes on one application, other nodes, and they'll do a special scheduling for some applications that want to run the whole supercomputer at once, right?
Are those 2 systems the only Exascale system so far?
The answer is, or the question is are they the only 2 today? They're the only 2 that I'm aware of with double precision. Now the Aurora system made by Intel at the lab in Illinois, remember it's the lab, Argonne, yeah. Argonne has the Aurora. They're using, if you count the number of single precision or integer operations per second, which again is important for AI applications, right? So they're at Exascale as well, 10 to the 18th operations, 10 to the 18th or more per second. So, but you know what? That's a good question. Are those the only ones? Those are the only ones that we see in the top 500 that you see. The AI superclusters out there are going to just dwarf what HPC has been doing. They are going to be massive systems of much larger size than Exascale. They have a lot of the AI training models are almost embarrassingly parallel, so they can leverage all of those systems, all of those racks of computers. So they'll, I answered your question as of the last top 500 machine, right? But there'll be a few more for simulation and things that will actually go in a top 500. Top 500 only measures double precision operations per second.
Here's that you're projecting again. I don't know if we're up to speed.
For some reason, this
He doesn't
white
like that white slide.
Yeah, it doesn't. And I'm going to go back, because I talked through the white slide already. I think I've got that. All right. So there are people who believe that there's a trade-off between getting the best performance out of a GPU system and programmability. And so that's where we're going to talk a little bit more about programmability. The kernel-level GPU programming skills, whether you're doing tiling, you have to deal with memory coalescing, atomics. There's a lot of extra stuff to try to get the optimal amount of performance out of these systems. And this is where CUDA and HIP are doing, right? I would disagree. I would say that now, I mean, initially it was true. OpenMP performance that you would get was not as fast as you could get with low-level, grid-level programming like CUDA or HIP, right? But I think today we're getting pretty close. We've spent a lot of time getting the generation of optimal kernels. Remember I showed you the target region? Well, what the compiler is doing, it turns that target region into a kernel. And in that piece, it actually launches that kernel. So you don't have to, in grid programming, you write a kernel, and then you also launch the kernel on a multi-dimensional grid. So anyhow, this is showing that at one time we thought that we could, the kernel-level programming was like assembler, right? You can get the most performance out of it. But I don't really believe that anymore. I think we can do a lot of automated compiler-assisted acceleration. All right, so this is it. This is on the left here. You see the hardware view of things, and the compiler in the runtime is mapping those 5 dimensions. Now, in the case of Oak Ridge and a lot of Livermore systems, they don't deal with device-level programming. How do they get rid of that? How do they do that? What they simply do is on the node that has multiple devices, like 4 on Livermore, 8 on Frontier, they just run more ranks. They bind the rank to the right CPU, and so each rank has its own, or each process on the node is going to talk to a different GPU. So each rank is on a different GPU. So they can kind of get rid of the one level of devices. Okay, but you still can't leverage the shared memory that you can have between devices on these machines. It's page migration, right, between those. So, but also, a lot of times they're not really running with groups of MPI ranks either. They're not using MPI in an advanced way. And it makes it difficult to kind of scale your application without addressing the number of groups. But you still have to deal with teams and threads. The team model, you have to do that. Otherwise, you won't get multiple work groups running in parallel on your application. Right? You know, when we did the team model in the OpenMP standards group, it really was there to map to work groups for GPUs. It's what, we try to make the standard leverage the existing GPUs. Intel liked it a lot, right? They found that they can group their threads into teams for different sockets. So in these high multi-socketed servers, right? And you want that to kind of leverage the NUMA to try to make sure that you deal with the NUMA effects of the memory for that socket versus the memory for another socket. So they actually end up using the team. So I'm really trying to tell you that don't worry about team. This is what's necessary. I'm that old that before we even had distributed memory multiprocessors with MPI, right? There's a lot of people up front said, because I worked at IBM where we had mainframes with shared memory and all this stuff, they said that's just too complicated. Application programmers will never do it. History shows that application programmers, and all you guys can raise your hand for MPI, understand how MPI works. So we're at that point today that we have to decompose domains to deal with teams of threads. And by the way, we'll get to wrapping there. Let's see. Cool software, right? This is my Hello Exascale world, right? My Hello World application. And this, I have to wait for it. Okay, so this thing was launched. The Hello World is launched an MPI, so it already has a rank. Each process has a rank. We know the number of ranks. And we're going to program the devices, the teams, and the threads. And we're going to print out a message. Hello, world, from rank 0 and of so many ranks. Right? That's what we want to print out. And we have to put a filter in it so we don't, if you did so many billion printouts, it would take forever just to print the parallelism. So we kind of put a filter on, say it's only when the rank number is, when the index is 0, print it out. Okay. So if you go walk away with anything, think, okay, if I'm going to go work on an application for Exascale, you're going to have to do some domain decomposition of this application, right? And it's going to be multi-level. It's not just saying, one rank per one atom per rank, right? So here we're going to print out, and it keeps going away. I'm going to see if I can get one quick slide in and get a number. So what you do is you multiply the number of items at each of those levels, and now that should get you to 10 billion way or parallelism. So you can see we multiply those out, and okay, is this my laptop, maybe? Is it HDMI connection to it?
Well, let me try something.
See if we pull this out, reset it.
Well, I don't think it's not that.
I'm going to reset it. There it goes.
I think it's the resolution coming out of your laptop. Change that, sure. You want to change it back.
Yeah. Okay. So there's a lot more to this Hello World application that I wrote. So that tell you, just to show you, and it really is genuinely a bulk synchronous, which you're not going to get a lot of performance out of it by having the synchronization unless you have a lot of work to do in each of the iterations, right? So, yeah, let's see. I think the next topic here, beyond the, so it means it's going to show a printout of a simulation of the El Capitan supercomputer at Lawrence Livermore, right? And the other thing that you multiply by is 2, because you almost always, to get to Exascale, you're doing some kind of multiply and add, right? A matrix multiply or a matrix solver. And so these machines, the instruction set of the GPUs, can do a multiply and add in one cycle. So that multiply and add counts as 2. So you can just multiply it by 2. We call that IPC, your instruction parallel. So you get this has an IPC of 2. I kind of just wrote along the side. The program that I have just prints out what's in light. And that's how we get 2.7 peak exaflops on the Livermore system, right? With over a billion way parallel here times 2.1 gigahertz gets you 2.7 gigaflops, double precision. All right. And the page before was the code that printed that out. Did you have a question? Does someone have a question here? I really wish we wanted more engaging. Any questions, you certainly can just interrupt me anytime. All right, let's take a look at the OpenMP programming model versus grid. The things we talked about earlier, CUDA, HIP, OpenCL, SYCL, these are all grids programming. When you write the code for a lane in a separate function, you write this as if it's running just a lane, and it's kind of like MPI, that you launch the kernel and you query what is my thread, what is my work group, X, Y, and Z coordinates. You have all of these things you query to determine what it is you're going to do on that thread. Right? So that's what grid level programming is like. You also must explicitly copy. So those people who know CUDA know you got to do a CU mem copy, right? Whereas in OpenMP, you declare the mapping of data structures and how the data structures are used. right? Mostly those things are C++ variants, right? The OpenMP, we annotate existing code. So we're annotating the code with pragmas that describe the parallelism, but you don't really typically change it's a bit of a lie here, that you don't typically change your host code. One of the reasons that we found early on why you have to change the code, and you have to do it as well for grid level programming, you really have to do the memory coalescing. This is really important, to not have a loop that jumps, that the different iterations of the loop access data that's far from the previous iteration, because the GPU is going to load a whole bank of memory at a time. So that memory coalescing is something that performance programmers of Exascale will learn to organize their data in ways so that it's coalesced and you get good performance. Okay, this is ease of use, right? This is the code for reduction in OpenMP. You just declare, I'm not going to use the pointer, okay? You declare the reduction in your pragma, and now you're updating the sum, which is this. Now, how would you do this in parallel, right? How would you update, how would a novice programmer go about creating a reduction? Array down to a single value. Typically, you're going to use an atomic operation, right? You're going to say, I want to atomically update sum, right? That's not a good thing to do, right? Because it would mean all of those parallel threads would be going for atomic access to a variable, and it would be slow. So typically, what you do as a grid programmer in CUDA, you're doing a reduction, you do pairwise sums, and logarithmically bring a large vector down into a single item, right? So I'm going to show that, how they do it, benchmark. Vote here. Who thinks this is easier, okay, than OpenMP? So, of course, in a grid level thing like SQL or CUDA, you have the host code that's going to launch that's C down here, DOM3 HIP launch kernel, right? There's a CU launch kernel GGL for those. There's an equivalent thing in AMD or NVIDIA. And then, of course, you also have to copy the memory back, write the code for that. And by the way, this code is from the stream benchmark, right? They cheat, right? Anybody see how they cheat? Like this. They're doing the sum, the final sum, back on the host. They're outside the target region. So they really just basically did a reduction into each of this, into a sum variable for each of the work groups, right? And what you really need is you need that sum on the GPU for the next operation, right? So, and then again, this is the code on the right is the thing to make sure that all the threads are covered and the synchronization necessary to do a sum, to get a single sum onto, here's the sum, hit block index to be the thread sum. So, the other thing is a lot of people get it wrong. But I understand that. This is why library programmers are made a lot of money. You know, getting a lot of people use libraries to do this kind of thing all the time. So that's important. And a lot of our libraries at AMD, I would say most of the libraries at AMD are written with HIP, so which is CUDA-like, and that's what a lot of the programmers, especially those AI programmers that use in PyTorch or Python, they have a library of device code that they'll use, right? So, in fact, that argument about that OpenMP is friendlier than the grid languages, that was a great argument a few years ago, but now there's so much focus on performance in the AI machine learning space that the libraries, the development of GEM libraries is really the critical thing that's driving programming in machine learning today. So this is performance showing where our compiler was at one point. Let's see, this is the 2021, our OpenMP compiler versus our 2022 compiler, improved performance. And you can see this big jump here on dot product. That's because we coded an optimized runtime on the device to that compiler. Am I running out of time? How are we for time? 5 minutes? Okay.
Yeah.
Good. We're going to go faster here, right? I will skip completely the internals of the LLVM compiler. Come talk to me later. I love talking about this stuff. All right, this is a lot of stuff I've developed. All right. ROCm 7 is our software stack, right? Let's see. Compiler's over here. So the ROCm 7 stack includes the compiler, libraries, a profiler, a debugger, complex runtimes, support for this. This is kind of a stacked view, and you see a lot of different application software above it for ROCm. All right, let's see. So the other thing I wanted to get to quickly at the end of this is talk about some of our hardware, some of the things that are happening. The machine learning training is driving rack level solutions, right? So we're just going to see phenomenal sized GPUs, right? In fact, there's some people who want to do wafer scale integration. And then we're going to put those GPUs, multiple devices, in a single node. And we're going to have high-speed fabric between the GPUs within the node, right? This is what's happening. And then what that is very difficult to program. In fact, this is where you have to use a CCL, a collective communication library that will allow you to do things like all reduce, okay, across your whole cluster. Right? So I'm going to show you what NVL72, the NVIDIA's NVL7, this is what you see. It's called Grace Blackwell, right, up there. Talk about that. I'm going to skip through any of the details here, but it's a full rack solution, a single node. And this is the node there. You're going to get in that rack 72 big GPUs. Right? In that node. You're also going to have switch fabric in there for NVLink to connect each of the GPUs together in those trays. This is a bit more of that architecture on the NVL72. And this next chart is showing AMD's progression of our GPUs. Our MI, when you see the MI, that is our GPUs for machine learning. Okay? And it looks like we lost. All right, so I'll go through that too. The Exascale machine at Frontier used an MI200, right? Several thousand of those. That's the MI200. The MI350 is what was used, actually a 350A for used shared memory for Lawrence Livermore. The next generation for 2026 will be the MI400 series. Those are designed to scale at least, actually the scaling limit is more, but initially we'll be able to put 72 of those together in a rack, much like the NVIDIA rack. But ours is a double wide rack. Same sort of thing where the middle of the machine is populated with communication blades. And those communication blades are also allowing you to connect multiple racks together. That machine that I showed you, the NVIDIA 7200, I don't know what an AMD is going to cost, but that machine is priced at $3 million for one rack, right? So people are buying them, and I don't know what AMD's is going to look like yet, but at least the machine will have a very similar number of GPUs, and we're very focused on the communication libraries to be able to leverage all of that scale up, right, parallelism within a node. Right? Scale out, multiple racks, scale up, big node. Okay, look at, I'm going to leave this open for questions here. Maybe we can, so this is the 350, this is what you see. This is the generation that's in the Lawrence Livermore system. It's actually a special version of it called 35A. And this is what Lisa Su, our CEO, is showing in terms of pictures of the the machine that's called Helios, which is a single rack system, a single rack solution, right? On this machine, OMP get num devices, that thing you can run on the host will give you answer 72. What you're seeing today, the most that you'll see in today's systems are 8 and 6 4. The old, even the IBM system at Oak Ridge had 6 GPUs on a Power 9 node, right? So, but now you can see the amount of scaling. So this is what the world is coming to in terms of scaling solutions for machine learning, and there's a lot of new market there. So yeah, the technology, AMD acquired a lot of technology, networking company Pensando, so they're helping us build these enterprise grade switches on these racks. And we even bought a company that builds racks and builds, it's called ZT Systems, right? So all that is being used in this product. I'm not getting it forward now.
Unplug it because it was,
Yep, that's okay, I'll just try to hear
it was reducing it. Sorry.
So this is the Helios rack, some information about it, make sure I get all the important information. Oh, so the NVIDIA rack is using a proprietary communication between their nodes called NVLink. It was there for, it's been there for a while, but it's been significantly upgraded with better SerDes and things like this. What AMD is doing is working with other companies, including Intel and Broadcom, to develop a standard for high-speed communication within a node, and that's called UA-Link, right? So this next year's Helios machine will have some of the beginnings of UA-Link, but we're working to standardize that technology so that it's not, we're not excluded from, other companies won't be excluded from that market. So UA-Link is an important technology. Again, that CCL library will run across UA-Link. Any questions? All right. And I hate to leave the slides on. I hate to leave the presentation for questions. That just says questions. I'll put something useful in. It's my son Casey, or my grandson Casey, teaching him HPC.
Any questions?
Any questions?
Doesn't matter, it's about the picture or about his talk. Okay, any questions?
I have a question.
We'll get you a second.
You mentioned your work experience at NEAS, NES at the beginning, so I wonder, I remember that project was really ambitious to take part big structures to small components so they can test like one beam in one campus and another column in another one, so they exchange data. So from your point of view, are those challenges can be solved? I mean, there were a lot of challenges like latency, network issue, and also the error tolerance, all those problems. Do you think nowadays, with what you have talked about today, those challenges have been solved or made it easier?
Certainly. When doing any kind of simulation, there's an infinite demand. The more demand, the more processing power you supply, the more accurate your simulations will be. In the case of NEAS, there was two things that will still be problems today that they used. The mixed mode simulation that you talked about, where you had a shake table working with a simulation and controlling the simulation or taking the data from the simulation. So that mixed mode, that sort of hybrid operation is still being used today. I do know that this guy from Sims Frank, he wrote this thing called OpenSeas, which was a simulator, and that was really the other problem that kind of simulation had, and we still have that today, especially with Rodgers simulation, and that is multi-mode simulation, right? Where you have one simulation that's doing a building structure, and another one that's simulating the ground motion and the liquefaction of the ground. So both of those have to work together to kind of predict how a building would react, right? So that mixed mode simulation, we have that as well in terms of atmospheric modeling today, right? You've got an atmospheric model, right, which is a whole different thing than an oceanic model, right? And you got to mix them together to do some kind of prediction. So, but I don't know that that's necessarily say it's solved. It's still an area of research, including, I would say, the development of software that does that efficiently. Okay. This guy here.
Oh, that's fine, you can go first.
Okay.
Which guy? Name?
Yeah, I can answer the check. So actually, I have a question about compilers. You said what now it's a thick book containing.
Yeah.
Are the compilers implemented everything?
I'm sorry, I'm not
The
here.
compilers implemented everything in that?
No, that book is just a specification thing. I'm going to be honest about that book, right? Because I even got involved in that. As the committee that writes a specification, that book is the worst thing you want for writing software with. It is written for implementers of the compiler, as like me.
Yeah.
And it's very difficult to discern from there. What you really want to do is we also manage another book online on examples, right? So we have an examples document that implements examples to show how to do certain things. That is really just a terse description, believe it or not, how big it is, of the specification for how the compiler should respond for implementations of it. So yeah, it's for the implementers, not for the users. All right. Yeah. But there are other documents.
Mark?
I think that was a good question. Thank you for that, because good point.
Let me see, so I guess I had two questions. The first is you talk about a lot of communication libraries, right? And I know a big challenge there has been, at least in the early days, the deep learning trainings was you had a lot of different topologies, point to point, ring, all this stuff. Or is there like an assumed fixed topology you guys are working on? Or do you have this problem where they're going to vary a lot and you have to sort of target different topologies with different interconnect latencies and all of that scheduling as well?
Yeah, I think the vendor of the hardware has to be responsible for that. That's the one thing that you're going to get from rack level integration, right? As opposed to buying the Cray or Hewlett Packard's. I'm trying to think what they used on both Frontier. It was it'll come to me. But anyhow, they had so the Cray put their fabric on it. In this case, it was I believe it was a butterfly configuration. And when I built a computer, the Mira Nostrum in 2004, we used the Kloss network of MiraNet. So you're right that the library has to be aware of the network, okay, and any congestion issues that might come up as a result. So this is why the library development of the communication collective library is so important, because it has to be aware of the topology and the system that it's running on. So it usually comes with the system, and AMD is we have a fairly big team and growing on implementing the collection library.
Okay, so it's kind of like you guys are building that for the hardware as sort of a bespoke set of libraries.
Yes.
Because I guess I was very interested, one of the teams I worked with a while back was kind of dealing with that, and they said we can't handwrite all of these, right? So they really invested a lot in sort of automatically synthesizing communication primitives with varying latencies and various topologies.
Talk
that
into
they
the
could-
mic, Mark.
Oh, am I not talking in the mic? Okay, sorry, thank you. Actually using program synthesis for this rather than classic compiler technologies on that. So that was interesting. I guess the other question I had was on this investment in these very large specialized racks, really focused on maximizing sort of the GPU and minimizing the CPU for current training workloads. And I'm interested in if you have any thoughts on how that goes forward as people are investing more and more in these maybe reinforcement learning models where you're going to do a bunch of GPU training steps, but then you're also going to have rollouts which are using like a theorem prover like Lean or calling a bunch of code and then feeding back into the training cycle. Yes.
I think we're all a little bit lost. Can you get to the question?
Well, yes. So I was saying this is very interesting in the sense that it really shifts away from that GPU intensive and you really need a more balanced workload, right? are you kind of, I'm just curious, are we building like a hardware platform that is for last year's workloads?
No.
This other one
no.
rolls out and.
No, let me, just-
Okay.
you know, we're definitely in a heated race with NVIDIA on this. The driver is trillion parameter models, right? So we're trying to grow the number of parameters on a model. I'm not that experienced in the stack, but this is what's driving the full rack integration, which really is important, is to have the fabric within that. Now we have a chip-to-chip fabric. AMD has always had a very good multi or chiplet technology, but now it's got to come out of the chiplet and across the whole rack. So you'll actually see fabric boards in the rack connected, and it's also why, you know, it's a good thing to invest in copper. Okay, you don't want the latency to do the, you know, you may like the bandwidth that you get out of fiber, but the extra latency could be a problem. There's also a lot of photonics research going on as well, but initially both NVIDIA and AMD, I think, are going to see a copper backplane on that to get the low latency and the high bandwidth. Right. Next question. These are great questions.
We still have time for maybe one or two questions.
You made me think of something. You used the word synthesis. You saw the target region right there, and then it said had parallel 4 within the target region. What have we been doing for all these years? We have been making the compiler look at that target region and synthesize a kernel for that. And then we generate the runtime that launches that kernel. So the launch kernel thing. So that's the intelligence that's going on inside the compiler to generate an optimal kernel to get the speed out of the system. So it definitely requires an intelligent compiler beyond what you would see in CUDA and HIP. CUDA and HIP, what are they doing? They're just mapping the written kernels to the actual hardware, right? So it's kind of like assembler. It's a little bit easier to do than to use an OpenMP application. So we can do it. It is synthesizing kernels. It's doing it much more efficiently. We have a whole team, a whole department of people just focused on performance of those. We have techniques called big jump kernels and a bunch of different things going on and getting good performance out of that synthesis layer that's needed. Okay. Do you have a question or any more questions? One more question?
Any questions?
I have a question for you all.
You still have a...
Your research is, so after when we have cookies, you can talk to me about the kind of stuff that you're working on here.
You can talk to him after.
Yeah.
All right, let's thank the speaker for his very interesting talk.